Hi everyone. Welcome to Step 7 of the MEDomicsLab testing phase. In this step, we are going to use two modules from two different layers. Firstly, we will evaluate models from the last step using the evaluation module, which is part of the development layer. Then, we will apply a model on a new patient from the holdout set we obtained at the end of Step 4 using the application module, which is part of the deployment layer. At the beginning of this step, you should have a time point folder in your data folder. This corresponds to the folder we provided you at the beginning of Step 6. It contains a holdout folder and a learning folder, each one containing 4 CSV files. You should also have a models folder, which you need to place in your experiments folder. We provided you with this folder at the beginning of Step 7, and it contains 2 MEDmodel files. If you double-click on a MEDmodel file, it opens a new tab in the app, displaying information about the model, such as the required columns for making predictions with a dataset using this model and the target column. In the future, we intend to implement more information in this file, such as the pre-processing steps, which are the steps taken on the data using the design layer. If you're wondering where the models come from, the first model, which is an extra trees classifier, is the model we created and saved in the second scene of the last step. The second model, which is a random forest classifier, is a model I specifically created for this step. Its purpose is to enable you to compare two different models using the evaluation module. The columns I chose to train the model on are the same as the model we created in Step 6, but the chosen options are different. For the dataset node, I didn't specify that the index was the subject_ID column, and I didn't clean the data. The result of this pipeline is the best model from the Picaret library, considering the AUC metric on our data. The results from this pipeline are slightly different from the Scene 2 pipeline. We have an AUC of 0.72 for the cross-validation result, instead of 0.70 for the Scene 2 pipeline. Additionally, the resulting AUC on the test set is 0.55, compared to 0.61 on the Scene 2 pipeline. Let's start by creating an evaluation. Click on the evaluation icon. Then click on Create Evaluation Page. Enter ET as the name of the evaluation for the extra trees classifier model. Enable the MEDomicsLab standard format option and press Create. The evaluation has been created in your workspace with the .medieval extension. Double-click on this file to open it. You will need to configure the evaluation page by selecting a model and datasets to apply the model on. Select the extra trees classifier model that we provided you at the beginning of this step, and then choose T1_holdout_modified and T2_holdout_modified as the CSV files to evaluate the model on. We select only these two files because our model was trained on T1_learning_modified and T2_learning_modified. Once the options have been set correctly, you can click on the Create Evaluation button. This will generate the model's predictions on the holdout set and an evaluation dashboard. This process may take a few minutes to complete. The Prediction tab displays the predictions made by the model on your holdout set, consisting of the columns you selected during the model creation step. The last 3 columns include your original target column, representing the true target values of your dataset, the prediction label, indicating the target predicted by the model, and the prediction score, which represents the probability assigned by the model to the predicted target. For instance, a row with a prediction label of 1 and a prediction score of 0.53 indicates that the model assigns a 53% probability to the target being 1. Here, you can observe that our model isn't performing well because it predicts only 1 as the target, whereas we have an equal distribution of 50% for both 1 and 0 in the true targets. Let's open the dashboard. The dashboard is constructed using the Explainer Dashboard library, which is a tool for rapidly creating interactive dashboards to analyze and explain the predictions and operations of scikit-learn-compatible machine learning models. It provides numerous interactive plots to assist in comprehending our machine learning models. There are several tabs in the generated dashboard, and we will explore each of them to examine the data we have. We will introduce many of the key elements you can find on the dashboard, but we encourage you to conduct further research if you wish to fully comprehend the dashboard's results. Let's start with the Feature Importances tab. Here, you can find the SHAP values plot, which displays the average impact of the variables on the predicted target. You can see that for our model from the last step, the most important feature is the maximum mean corpuscular hemoglobin concentration (MCHC) attribute from the TS lab class at time point 2, followed by another attribute of the TS lab class at time point 2. You also have another plot available related to the feature importance, which is the permutation importances. This plot measures the increase in the prediction error of the model after we permute the feature's values, thereby breaking the relationship between the feature and the true outcome. In fact, a feature is deemed important if shuffling its values increases the model error because, in this case, the model relied on the feature for the prediction. Here, we can notice that attribute 5 from the image class at time points 1 and 2 are important features for our model, while attribute 7 from the image class at the 2 time points doesn't seem important in the model prediction as shuffling its values didn't affect the model performance. However, as our model isn't performing well, our observations must be taken carefully because the increase in the model performance can be a random effect. Now, let's shift our focus to the Classification Stats tab. This page displays several plots. At the top of the page, you have 2 metrics that you can adjust for all the plots, which are also available in each plot independently. The cutoff prediction probability acts as a decision boundary. If the predicted probability for an observation exceeds this threshold, the observation is classified into one class. Otherwise, it is classified into the other class. It is set to 0.5 by default, which is optimal for us because we have an equal distribution of zeros and ones. The cutoff percentile of samples labels the top selected percentage of the highest scores as 1 and the remaining as 0. The model performance displays the same metrics that you can find on the learning module for your learning dataset, but applied to the holdout set. In fact, you can observe differences in the metrics between the cross-validation step, the evaluation on the test set, and the evaluation on the holdout set. It's important to note that the AUC from the learning module refers to the ROC AUC. Right next to this, you have the confusion matrix, which displays the percentages of predicted classes compared to the true classes. Here, we can see that the model predicts only 1, even when the observed class was supposed to be 0. You can try modifying the cutoff prediction probability to observe its impact on the results. We can observe that even after changing this parameter, the model does not appear to perform well. You can also assess the impact of changing the cutoff prediction probability on the model performance metrics. If you scroll down, you will have access to a precision plot, which shows the percentage and counts of ones depending on the predicted probability. The predicted probability refers to the prediction score column on the Predict tab. In fact, you can see that the majority of the prediction scores fall between 0.5 and 0.6, indicating that the model is not certain about its predictions. The classification plot shows the distribution of labels above and below the cutoff, indicating that those below are labeled by the model as 0 and those above as 1. Here, all the labels are above the cutoff, meaning that they are all labeled as 1. You can interact with the cursor below the figure to observe the impact of changing the cutoff on the distribution of labels. At the bottom of the page, you also have 2 AUC plots, a ROC AUC plot and a PR AUC plot. The receiver operating characteristic curve displays the true positive rate against the false positive rate. The PR curve displays the recall against the precision. As before, you can use the cursors below the figures to see the impact of changing the cutoff prediction probability on the figures. Right below, you have 2 other plots. The lift curve displays the number of elements labeled as positive on the y-axis, considering the percentage of elements sampled in decreasing order of true label. The plot shows the perfect curve, the model curve, and a random curve. Observing the perfect curve, you can notice that at 50% of samples, we should have 100% of the true 1 labels labeled as 1, because we have 50% of 1 in our data. But here, you can notice that our model is very close to the random curve. It randomly assigns label 1 to both 0 and 1 classes. The cumulative precision plot as stated in the explainer dashboard library documentation, is a slightly different representation of the lift curve. Let's now focus in the Individual Predictions tab. This tab displays several plots that allow you to evaluate your model through individual predictions. It enables you, for example, to observe the contribution of each individual in the prediction. The first section allows you to select the index of the individual you want to analyze. You can either choose an index from the list or select a random one using the Random Index button. Additionally, you can filter the indexes you want to observe using the selectors in the Select Index section. For instance, you can choose to display only the indexes with a true target of 0. As you update the Selected Index section, you'll notice that the prediction plot updates accordingly. It displays the probability that the model will assign to each class for the selected individual. As we noticed earlier, the majority of individuals are labeled as 1 by the model with a probability between 0.5 and 0.65. The contributions plot shows you the contribution of each feature to the prediction of the selected individual. In yellow, you have the average prediction of the population. In green, you have the features that increase the prediction probability. In red, the features that decrease the prediction probability. And in blue, the final prediction. Here, for example, you can observe that the MCHC maximum attribute from the TS Lab class at time point 2 increases the prediction probability significantly. We can make a link with the SHAP values plot where this feature was the one that had the biggest impact on the prediction. The partial dependence plot shows you how the prediction changes when you change a feature. You have a plot for each feature, where the x-axis represents the possible values of the feature observed in your data, and the y-axis represents the predicted target in percentage. Below 50%, the target is 0, and above 50%, the target is 1. You can observe each feature independently for each individual. You can see that in a few cases, our model could have predicted 0 as the target if the value of the observed feature was slightly different. However, in the majority of cases, even if the value is different, many features would never change the predicted target with our model. The last plot on this page refers to the contribution plot, which displays the values of the feature's contribution to the prediction for the selected individual. The What If tab consists of the same sections as the Individual Predictions tab, except that you have all the selected individual features values in the middle of the page, and you can update these values to see their impact on the prediction. Similar to the last tab, you can observe that if some features had different values, the model could have predicted 0 as the target. This tab can be very useful for detecting which features are useful or causing problems for the model. The Feature Dependence tab shows you the SHAP summary and SHAP dependence plot between all the features. The SHAP summary is the same plot that we had in the first tab, so let's focus on the SHAP dependence plot. The SHAP dependence plot displays the value of the first selected feature on the x-axis and the SHAP value of this feature on the y-axis. The second selected feature is represented by the color on the plot, with the color scale shown on the right of the plot. The third input, index, allows you to locate which index on your dataset corresponds to which point on the plot. Here, we didn't find any noticeable dependencies between our features. Let's open the Feature Interactions tab. This tab also shows you a SHAP summary plot and a SHAP dependence plot, but these figures are different from the previous tab. Let's begin by explaining the interaction dependence plot. This plot displays the value of the first selected feature on the x-axis, and similar to the plot in the previous tab, the value of the second selected feature is represented by the colors of the points. The difference with the feature dependence plot is that the displayed SHAP values on the y-axis represent the SHAP value between the two selected features. In the previous plot, the SHAP value was the value between the first selected feature and the prediction. The interaction summary plot shows you the SHAP interaction value between the selected feature and all the other features, ordered by the most important value. Using the two plots, you can notice that there don't seem to be any features with strong interactions. The SHAP interaction values are often less than 0.05. Here, we won't explain the last tab, Decision Trees, as it doesn't provide useful information about our model and can be difficult to understand and confusing in the context of our model. Let's create an evaluation page for the second model. Since I've already described most of the available plots in the first evaluation, we'll just take a quick look together at this second evaluation. However, you'll be able to explore the entire results on your own. Click on the evaluation icon to make the Create Evaluation Page button appear. Then, press this button, enter RF as the page name because the second model is a random forest classifier. Enable the MEDomicsLab standard option and press Create. A new .medieval file will be created in your workspace. Double-click on this file to open it. Select the random forest classifier model that we provided in the model section and T1_holdout_modified and T2_holdout_modified in the dataset section. Press Create Evaluation. If you observe the predictions, you will notice that unlike the first model, this model does not predict only once. At first glance, you may think that this second model is performing better. However, if you look at the prediction scores, you will see that sometimes the model has high prediction scores, like 0.7, 0.8, or even 0.88. As a reminder, the majority of the prediction scores for the first model were between 0.5 and 0.65. The problem is that, upon closer inspection, many predictions are inaccurate. For instance, here, the model is 88% certain that the target is 1, but the true target is 0. Let's take a look at the dashboard. If you observe the feature importances plot, you will notice that the features that are the most important for our second model are different from the ones we've seen in our first model. Let's open the Classification Stats tab. Here we are going to take a look at two plots to evaluate the performance of our model. Let's start with the confusion matrix. By observing the ratios between observed and predicted values, we can notice that our model doesn't seem to perform well at all. Among the true ones, 7 were predicted as 0 and only 6 as 1. If you add the percentages from the matrix, you will observe that 46% of the predicted values are wrong. Let's now focus on a second plot, the lift curve. By observing this plot, you can notice that our model is really far from the perfect model and really close to the random model. Feel free to examine other information from the dashboard yourself. Here, all the information that we analyze seems to indicate that our two models are not performing well. They are predicting almost randomly. We think that perhaps we included too many columns to train the models on, compared to the number of patients we have, and the models failed to train effectively. Perhaps using fewer columns to train the models will help us obtain better results. Let's delve into the final module of MEDomicsLab, the application module, which is part of the deployment layer. We are going to apply one of the previous models to a patient from the holdout set. Double-click on the application module icon. This will open a new tab. The first thing you will have to do is to select a model. Here, I choose to select the random forest classifier model. Once the model is selected, you will need to enter your patient's information based on the columns the model was trained on. We will apply the model to a patient from the holdout set. Since the model was trained using data from time points 1 and 2, let's open the CSV files related to these time points, T1_holdout_modified and T2_holdout_modified. To apply a model to a patient, we need to fill in all the fields. Therefore, we need to select a patient who doesn't have null values in the required columns. Let's select the fifth patient from the CSV files. Then, let's copy and paste all the information into the Application tab. To easily locate your patient's row, you can freeze the subject ID column by selecting this option in the top right corner of the column. This will keep the column displayed while navigating through the data table. After entering all the information, click on the Predict button. This will calculate the prediction for the patient. Your results will be displayed as a table row, containing the information you have entered and the predicted target. Here, the model predicted 0. If you look at the target from the time point CSV files, you will see that the true target was 1. In fact, as we mentioned while evaluating the model, it does not perform very well. Well, we have now explored all the modules of the MEDomicsLab application. In the next step, which will be the last, you will have to create a model by yourself, as we did in step 6, with the goal of achieving the best possible model. The data for this step will be slightly different as we will merge the learning and holdout data from this step into a new learning set, and you will not have access to the holdout set we will create to evaluate your model. See you in the final step, which will be the challenge.